Well, I figured out how to make a solid-state version of Joseph Newman's motor. I was sitting here in meditation, not paying much attention to the mantra, just thinking thoughts, a lot of thoughts, and I came to the conclusion that Edward Leedskalnin's perpetual motion holder has a lot to offer to our analysis of the Joseph Newman motor. So much so that it basically does the same thing, but you have to set it up. You have to charge the toroidal magnetizable mass. Let's say it's the core to a transformer, using coils wound around that toroidal transformer core. You have to input energy to get the magnetic flux to start spinning around in the circular shape of that toroid. Once done, though, you only need an instant. It's a lot easier than trying to magnetize a bar magnet. My God, the energy required to magnetize a bar magnet is humongous. You've got to raise the temperature several hundred degrees, I don't know, Fahrenheit or Celsius. Then you've got to induce a magnetic field and keep it in that field while you gradually lower the temperature until it's at room temperature. Then you can shut down the magnetic field, and now you got yourself a permanent bar magnet that's going to last for maybe a few centuries before it starts to really have lost, a sizable portion of its power. But it loses it. A perpetual motion holder never loses it unless you extract it. And in Joseph Newman's motor, there is no energy extraction going on such that the magnetic field of the spinning bar magnet becomes reduced. It doesn't happen. All you have to do is keep it spinning. And it's spinning because it's on the axis of the commutator. But with Leedskalnin's situation with his perpetual motion holder, he didn't invent it, he just popularized it. Somebody else invented it way back in the 1800s. But so we started with an instant of electrical power of coils wound around it, and then we removed the coils. So this is like removing the magnetic field from a bar magnet. But see, we have internalized that magnetic current. It's inside the perpetual motion holder. It does not come out. So it kind of makes you wonder, how can this work? Well, the coil that we use to charge that toroidal shape is the same coil. No. Can't be, can it? I don't know. I think there's I'd like to think there's a possibility here of a solid-state version. Maybe it is the same coil that we're going to use for the Joseph Newman motor. Only now we're going to charge that coil. Well, see, no, you can, oh my God. Oh, I'm sorry. All right. Now I got it. The energy we use to charge the toroidal core, the iron toroidal mass, the magnetizable mass, has to be AC. That doesn't make any sense. Then it's not perpetual motion. Oh dear. Oh, you get two of them. Two toroids, and you set it up, with the DC pulse, a little spark, to get each one going, and then you flip them and put them sandwiched together so that they're going in opposite directions relative to each other. And now you've got yourself an AC system, but it's DC. But it's not chopped up. So it's still internalized. How do you get it to externalize? Well, because now your coil, the Joseph Newman coil, has to be wrapped around that toroidal shape. Now the toroidal shape does not have to be a circle. It just has to be circular. So it could be rectangular, just so long as its entire loop is magnetically coupled to create a solid magnetic loop, so that the magnetic force can go around and around and around inside that magnetizable mass of iron or whatever it is, nickel, whatever we're making the magnet out of. It could be a neo ingredient recipe for a magnet. So the energy is going around and around. We got two of them going in opposite directions, and we have the Newman coil wrapped around both that are sandwiched together. And of course it's a massive coil. So actually we do have to assemble it. We have to charge up those two toroidal masses and then disassemble the wire that was used to charge them up with a DC force, and then rewrap it with the two of them sandwiched together with a huge singular coil. And now we can hook up that coil to a DC source, but in order to chop it up into a square wave, we're going to have to use solid-state circuitry to do it, because we don't have a rotating shaft anymore to rotate a commutator. So we've got a solid-state timing switch or something, optocouple, I don't know, something to chop up the DC into a 50% duty cycle. And then we've got to have another switching device, just like my simulation, to self-short the coil for 20% of its duty cycle during the last 80 to 100% portion of its duty cycle. And then we put in a little spark gap with a very low voltage breakdown, maybe a vacuum tube, a high voltage vacuum tube, because a neon bulb doesn't have the caliber of tolerance for high voltage that we're going to need. But we will need a low voltage breakdown so that it can start, a spark gap normally has a voltage breakdown minimally of 1,000 volts, and that's way too high. So we want it down at 100 volts, which is why Newman put a fluorescent tube in a secondary coil wrapped around the primary. But he isolated it. I'm not sure why. And it barely flickered, but it did enhance the performance of the coil. So it shows that my neon bulb will work. It's just, actually a neon bulb has a lower breakdown voltage. He never thought of using that. But the fluorescent tube probably has a higher tolerance for high voltage than does the neon bulb, and that's probably why he used the fluorescent tube. So that's its caveat. But in the ballast section of one of the ways to get a fluorescent tube to light up is to use a neon bulb as a starter mechanism, because once the neon bulb starts to function, then you can raise the voltage sufficiently to break down the breakdown voltage of the fluorescent tube. So actually it might be useful to put a neon bulb in line with, if we can find a ballast that uses a neon bulb, because there are different ways of lighting up a fluorescent tube, but if we get one that has a neon bulb methodology, then what happens is the circuitry somehow disconnects the neon bulb at some point when it's no longer needed, once the fluorescent tube starts to light up, and then you save the neon bulb for future use, although you don't have to if you just keep replacing it every time you want to turn the thing on, or the whole contraption on. But now you've got your breakdown voltage, so you've got your increased amperage flow that will now reach the breakdown voltage point of the fluorescent tube. And once that lights up, now you've got yourself a fully lit fluorescent tube that will really magnify the operation of the coil. But I don't see why it has to be isolated, because in my simulation I put it in line with the coil and the coil's capacitor. The capacitor is in parallel with the coil, and then off to one side of those two juxtaposed sandwiches that are opposing each other on a closed loop, the spark gap or neon bulb, whatever, can be placed somewhere on either side. So it's three sides of a square, or it's a triangle basically, triangular circuit, but it's a sub-circuit off the DC supply coming from the battery pack that's powering the coil for 50% of the time. So that sounds like it's a good improvement there, but now we've got this solid state spinning magnetic field going in two directions simultaneously which is a semblance of AC. It's about the closest I can consider bringing this to a head, unless, well, no, I can't imagine how else to do this. So now we've got the Newman's massive coil wrapped around these two sandwiched perpetual motion holders that have opposite orientation of their magnetic field that's inside them. And one thing I've learned about simulation is that every part of a circuit sees the energy in every other part and responds to one degree or another depending on how well, depending on the net electrical activity at that component, because all these electrical influences coming from the various components of a circuit are influencing each other, changing how electrical energy manifests within each component. That's the net result. But what we don't see is that there's all kinds of conflicting energies sloshing around in opposite directions, same direction, different values, and it's a truly complex waveform that goes on inside a circuit. But the net result is all we see. You know, the net volts, the net amps on every single component, the net waveform. That's all we end up seeing. But it's really far more complicated. And that's what's going to be happening in this Newman motor. So I'm not 100% sure this will work, but I thought it was an aha moment because I thought, oh, cool, but what do I know, right? So it's an idea, but it would really help because whenever you switch to solid state, it's always better. And it improves efficiency, performance. You don't have... That's one loss right there, mechanical loss, that goes out the window. You don't have to worry about it. And there's no resistance to magnetic flux. That's why when in my simulation, I try to reduce the simulator requires that I put resistance on a voltage source, and so I put a very small amount, like a pico ohm or something, just to make the simulator happy. But in reality, there's no resistance in a perpetual motion holder, or else it wouldn't be perpetual to hold a magnetic charge. But it is internalized, and that's what I'm worrying about, whether or not this will work. Because a perpetual motion holder internalizes its magnetic field. It does not allow it to escape, because if it did, it would dissipate, see? So it never escapes unless you break the loop, the magnetic coupling, or you input an equal or greater force in the opposite direction, which means now you're carrying that toroid into the second phase of an AC cycle. You're creating an AC situation at that point. And then it'll release the prior energy when you put in the next one to replace it going in the opposite direction. And that's how an AC toroidal core to a transformer works. It's really two DCs, and that's how you're able to get the magnetic flux to leave, is because you're putting in another one going in the opposite direction. And whatever. Anyway, it's almost as if magnetism is not the same as electricity, in the sense that electricity you blend. But with magnetism, it's almost as if it's exclusive. It's an exclusive situation in which you can only have a single vector of magnetic flow, and it can only be going in one direction at one time, at any one time. While with electricity, you can have it going in so many different directions in different strengths simultaneously, and then we just measure the net result. I think that's what it's looking like in terms of basic physics theory of the two. The difference between magnetism and electricity. That's a major difference, very big time. And I think that's why it might be possible to make envision making a solid state of this. I know from John Bedini already, and somebody from Canada reminded me, a YouTube commenter, that you can always make a solid state version of a mechanical device. It's just, you got to really know what you're up against. You really got to understand what you're doing to be able to do that. You have to thoroughly, completely understand what you're dealing with. John Bedini was able to take the Tesla switch and turn it into a solid state device. He didn't need anything mechanical, and it was very efficient, and the output performance was very much enhanced. because that's the way solid state is. So it could be now I've figured out how to make a solid state version out of this Newman motor, because it's not a complicated circuit, you know. It's just a question of coming up with that aha moment and take what we already know and create a marriage of a new idea with the old idea. And Ed Leedskalnin's perpetual motion holder has a lot to contribute to our understanding of the Newman motor anyway, as it is already. But little did I think I would apply it and marry it to the Newman motor. Little did I think I would do that. And that's what it looks like. So it would help if the magnetizable substance were made out of the same recipe as a Neo bar magnet. In fact, it wouldn't hurt if it was a ring Neo permanent magnet, now that I think of it. What do you think? You just get two of them and you... Well, they're not going to like being put together in opposite orientation to each other, that's for sure. They're going to want to push away from each other. They're going to want to repel, except if you... No, that's if you have them going in the same direction. If you reverse it, they're going to want to smash together. So you're going to have to be able to put them together without them breaking each other, because they're going to accelerate as you bring them closer and closer together. The magnet... In fact, it's impossible for them not to smash. I found that you have to put a layer in between, like bubble wrap, layers of corrugated cardboard, and then somehow, hopefully, try to remove those layers one layer at a time. Actually, bubble wrap would not work. Now, if you're trying to remove it, it would have to be particle board, let's say, or very thick cardboard. Lots of layers of thick cardboard, and removing one at a time. The problem being that the closer these two pieces get to each other, it's like a vice grip. It might be very difficult, unless you just burn the... No, you can't burn it. That would raise the temperature and you'd lose the magnetic force. Yeah, I don't know. Unless you have a very special vice grip that's holding these two things, and then you can remove the cardboard from in between them. Or plastic. It could... Well, no, plastic is too lightweight. Well, but cardboard's going to shred. You don't want anything in between them, ultimately. Yeah, we may want them to be magnetically coupled, smooth surfaces abutting each other. Wow, this is very fascinating. How do we... It won't be easy. It's going to be a technical difficulty, but I bet it can be done, and we won't have... It'll be very strong. It'll be a neomagnet. That's pretty powerful. Why not? Two ring-shaped neomagnets sandwiched together in opposite polarity. They're going to want to smash together and create a very strong bond, magnetic coupled bond, and then we wrap our massive coil around it. Now, our coil is going to be different. It's not going to be this standard Newman coil. It's going to be a toroidal-shaped coil. And the ring is going to hamper how big the coil becomes because of the size of the opening of those magnetic rings. So what we may have to do is avoid a solid toroidal ring and just do two halves of a ring. You know, like you take a square ring and it's split down the middle. So those four C magnets could be pre-charged, to become permanent magnets, and then we join the two C's together to create a toroid. After we've already wound, there you go, it could be just 8 segments. 8 rectangular lengths segments, each having their own coil. And they're pre-magnetized, they're wound, and then we assemble them by magnetically coupling their smooth surfaces. Oh no, they can't be pre-wound. Well, no, actually... Well, okay. 8 bar magnets, bound in pairs. So we have 4 pairs. And the poles are at the ends, and they're twisted around when they're brought together. So the south end of one is laying alongside the north end of the other, and vice versa. So, and they're going to want to be bound together. So now we're dealing with four pairs of bar magnets, neos, and now we wind a coil around each one, and now we're going to have to bring the four pairs together at their ends, because the coils, they're bare at the ends. The coil only is in the middle section. And so now we're going to have four coils, and we connect the coils together to create a series connection between the four coils. And now we've got our massive single coil, but they have to be solder connections of those four coils. Certainly not not alligator clips. And now we've got one massive coil around two toroidal permanent magnets, neomagnets. And we've got most of the thing assembled. The only thing left remaining is some kind of solid-state switching device to create the DC switching for the coil, and then connect the coil to a DC battery pack of very low amp hours, but very high volts. Yeah, we want extremely low amp hours to prove the point that we're not running this thing on amps. We're running it on volts. And then we put in our capacitor in parallel with the coil as well. And we put in our little double spark gap, actually a neo followed by a fluorescent tube arrangement, to help the fluorescent tube break down and ultimately survive the high voltage, which the neo will not. And then there has to be a switch to disconnect the neo, short out the neo, so that we don't burn it up, because the neo is not going to be able to handle that much voltage. This is looking good. This is looking really good. This is looking excellent, in fact. It's always a good idea to get away from mechanical motion. So I'm sorry you're staring off into space, but it was dark there at first. Oh, it's still dark. Yeah, there's nothing to look at, so I'm just recording my voice. So this is looking good. Now all I have to do is nothing. I share this with you. Oh, joy for sharing.